The Standard Model is the most widely accepted theory in the field of particle physics. It includes all the observed elementary particles and describes the interactions between them. This includes the quarks and the leptons, responsible for making up all the matter we see, and the bosons, known as the force carriers, that are responsible for mediating the interactions. However, the Standard Model is not complete. It fails to explain the existence of gravity, dark matter, dark energy, and even the observed neutrino masses. For this reason, several experiments are being made around the world to both test the Standard Model and to try to find new physics beyond it. Collider experiments are some of the main drivers in this research. They use particle accelerators to accelerate particles to near light speed. These particles are then made to collide, and the results of their interaction are collected in detectors stationed near the collision point. The gathered data is then used to study the phenomena that resulted from the collision. Several kinds of particles can be collided in these experiments, but if the objective is to study the strong sector of the Standard Model, meaning the quarks, gluons and their interactions, in conditions of extreme energy density and/or temperature, heavy ions are usually the best choice due to their large quark content. These collisions create a very energy-dense region near the collision point, where quarks and gluons behave as nearly free particles. This state of matter is called quark-gluon plasma, or QGP for short. QGP is extremely short-lived, rapidly expanding and cooling down, which leads to recombination of quarks and gluons into mesons and baryons, in a process known as hadronization. This means that the QGP itself will never reach the detector, thus making it very difficult to study. There exists, however, a QCD object called the jet, created at the same time as the QGP and resulting from the decay of a quark or a gluon whose products reach the detector. If we can compare a jet produced during a proton-proton collision to one produced in a heavy ion collision, we will be able to see how the QGP affected the second jet, thus learning about the QGP itself. The difficulty now becomes the identification of the jet, or in other words, finding out which particle was at its origin. This process is called flavour tagging, and focuses on the inherent properties of each kind of jet to differentiate between them. B and C jets, for example, both present a displaced secondary vertex due to the long lifetime of the B and the C hadrons, respectively. During my thesis project, I will be working with one of the Atlas collaboration's most recent flavor tagging algorithms, called GN2. GN2 is a machine learning model characterized by having a graph neural network, or GNN, in its architecture, where each of the graph's nodes represents a track left by a charged particle in the detector. Another characteristic of the model are the auxiliary tasks of track origin prediction and vertex prediction, which have shown to better the results of the main task of jet flavor prediction. GN2 has been tested for proton-proton collisions showing good results, and this project aims to assert if its predictive power remains when accounting for the added complexity of heavy ion collisions. Thank you for watching.